we're going to take what we looked at in the previous video and we're going to take it a step further by finding the equation of a line of best fit. All right, and this is really going to be the crux of everything that we're going to be doing in this section. This is basically going to be the line that's closest to the data points that has the least amount of error. And it's actually pretty simplistic to find in MATLAB. So we're going to use this function, polyfit x comma y comma 1, where x and y are the row vectors. 1 is the degree of the polynomial. So we're getting a first degree polynomial, which produces a linear sort of equation. Now, it's not actually going to produce the equation. It's going to produce a row vector that have the coefficients of the first order polynomial in descending order of the terms in the polynomial. So this will be the first degree and then the 0th degree. And so I gave you a really simplistic example. And we didn't even need the sims in here, but I guess I cut and pasted from before. But if we have a vector x1 and a vector y1, then if p is equal to polyfit, then we could define the least squares equation as p1x plus p2. So this would be ax, which is going to be the coefficient of the first order, and then p2 is the coefficient of the 0th order or the constant. All right, so if we went into the previous example, remember we had the pressure and temperature, so temperature explaining pressure in the 1 kilogram of nitrogen. Let's find MATLAB code to find the least squares line. We're going to print the equation of the line to the screen. We're going to create a scatter plot. And then also we're going to plot the scatter plot and the equation of the least squares line on the graph. All right, so we're going to plot the line and the points just to see how far any of the points are. And then finally, we're going to do an extrapolation or interpolation where we find the pressure given that the temperature is 185 degrees Celsius. All right, so I'm just going to take the code that we had before. I'm going to start by defining a sims variable, and I'm going to call it LSEQU. All right, or we can even call it least squares line. And this is going to be able to utilize the equation of the line. All right, so that's why we need this. And down here, what I'm going to do is I'm going to define P to be equal to polyfit of temperature, pressure, and we're going to get a first degree or first order sort of polynomial. All right, now I'm just going to run this to show you what happens, just to make sure that way you can see the next step why we have to go through and define least squares line. So, all right, and what happens is we get the coefficients. All right, so this is, or we multiply everything by 10 to the third power. So this is going to be the coefficient of the x term or the slope. This is going to be the constant. All right, so what we're going to say is that LS line is going to be equal to P1 times X plus P2. All right, and it's going to look kind of ugly when we run it. Oh, I forgot to define X as a sims variable. So let's define X to be a sims variable as well. All right, and it looks kind of ugly. All right, and it is what it is. So, but that's our least squares line. All right, so we can print it out if we wanted to. And so I'm just going to do an fprintf, and I'm going to say the equation of the least squares line is, and I'm going to say %s. All right, and then I'm going to \n, and I'm just going to print out comma ls line. All right, so that should print out the equation. And remember, %s is a string. We don't want to print it out numerically because x is a symbolic variable. So if I run it, now I'm going to get this sort of statement here. All right, so it's not that pretty, but it doesn't really matter. Okay. Next thing we're asked to do is we're asked to go through and plot both the points as well as the equation. So I'm just going to cut and paste that code that I had before. So remember, this is our scatter plot. And what I'm going to do now is I'm just going to go through and define x1 And we don't need a symbolic variable for this, but x1 is going to be the domain of the least squares line. Now, you might remember that the temperature started at -40, all right? An easy way to do this is to make a vector that starts the lowest value of x given in the scatter plot, and then the highest value given in the scatter plot. So what I'm going to do is I'm going to say x1 is going to be the minimum of temp. And we already, I mean, clearly we can see that that's -40, but in a larger list of data, it might not be easy. We're going to see 0.01 is going to be the increment, and we're going to say the maximum is going to be the max of temp. All right. Now I'm going to say y1 is going to be equal to the equation of the least squares line. All right. Now we have to be careful with this. Let's check this out. If we do p1x, so p1 times x plus p2, we're going to get an error. All right. And I'll show you why. So I'm going to run this. All right. Or in fact, it didn't give us an error. Sorry. And I think it's just because it's a constant times a singular value of x. Technically, we really should put the point in there. All right, so this dot right here. And what I'm going to do is I'm just going to go down here, and I'm going to put the hold on so we can plot on the same graph. And I'm going to plot x1 comma y1. All right, and that's just going to plot the vectors, okay, except it's just going to plot a whole bunch of them, and then I'm going to turn the hold off. All right, so that should give us a new graph. Let's see. It's telling us that we don't like this for some reason. So we're going to plot x1, y1. Data must be numeric. It looks like it is. X is symbolic. Oh, because that should be x1. That would be helpful, wouldn't it? There we go. Okay. So just a little bit of variable area error that some of you probably were screaming at me about while I was doing this. And now we can see a little bit better that almost every point is almost perfectly on that least squares line, which we'd expect with a correlation coefficient of almost 1. Now, there's a few of them that are just slightly off, all right, of not being centered, and that's okay, all right. Most data, it's not going to be as perfect or as close to perfect, in fact. Right. Now, the last thing that we have to do is we're asked to be able, and I'm going to just bring up the instructions again. We're going to try to find the pressure when the temperature is 185 degrees. Well, that's pretty easy because all we have to do is just substitute 185 back in for x. And so what I'm going to do is I'm going to say P185 is going to be equal to P1 times 185 plus P2. All right, and that's the equation of our line. And what we can do is a couple things. So we can say f print f, and we're going to say not f pront, but f print. That would be helpful. We're going to say the pressure at 185 degrees centigrade or Celsius is %F, right? And we're going to say that that's P185. Right? And another thing that we can do is we can actually plot it on the graph. All right, so if I wanted to, I could just move all of this down. And check this out. This is pretty cool that we can see our extrapolations. And let's plot 185 comma P185. And instead of using a circle, let's use like a different marker. I'll just say D. I don't know what D does. Might do a diamond or something like that. I don't know. So we should get a new plot in addition to the extrapolation. All right, so we get the pressure at 185 degrees Celsius is 13,592.559, whatever you want to call it. All right. And if we look at the plot, here's our extrapolated value, and it's clearly in line with our least squares line. In fact, if I want to go back into the code, I could just extend this right here instead of the max being the temp, and I could just say like 190 or something just to show that it falls on the line perfectly. Let me run this again just to illustrate this. And there it is. It basically is perfectly centered on the line. because it is on the line, all right, because we use the extrapolation to be able to predict it, all right. Um, so this is pretty cool because what we can do is we can differentiate between the original data and the extrapolated data or the predicted data if we were to utilize this sort of thing to be able to predict data. A lot of times predicted data is going to be useful to us, but we certainly want to make sure that we differentiate it, all right, when we're looking at this, because certainly if it's an original data point, it falls exactly on a line, that might merit a little bit more consideration to the validity of the model, as opposed to just having 15 points that we already know are on the line. All right, so for instance, just as one final example, we know something like 100 is exactly on the line. Okay, so I'm just going to say P100 is going to be equal to P1 times 100 plus P2. And I'm just going to plot the exact same thing, except I'm going to do 100 and P100. I just say P100 like prediction 100, and I'll use a diamond again. All right. And so, or I can use a square. Let's try S. I think S gives us a square. Let's see what it gives us. All right, so it does give us a square. And right here is that final point. All right. And clearly we can see that it's an extrapolated point or interpolated point. It's directly on the line. It doesn't mean as much to the predictive model, all right, to building the model. It certainly means something to somebody using it, all right, but that's pretty easy to see. I mean, most people that are scientists know that, okay, well, if you have 75 here or whatever it is, 80, and then 120 right here, then you could pretty much predict what's going to be in this. So just showing you, if you wanted to in real life, separate your points out, that this is a way that you can do it on the scatter plot and separate it from the original data versus the extrapolated or interpolated data. Okay, so next video, what happens if the data is nonlinear, but we can force it to be linear? All right, so we're going to take a look at how to do that in our next video.